Everyone who's having a good time at EuroPython. uh, I'm Vinayak, and today I'll talk to you about my project to run every street in Paris. So this is the general outline. I'll talk about my motivation to do something like this. We'll look at GIS and related concepts, how we can get data from OpenStreetMap, how we can store it in Postgres with PostGIS, and finally match map our runs to the street network to visualize our progress. Hopefully that'll give you like an overview about how to build a system like this to run every street in your city, or maybe to tackle similar problems to this one. A little bit about myself. I'm a software engineer based in Paris. I built a bunch of open source tools like Camelot, Present, Fleur, which some of you might have used. Most notably Camelot, which is like a Python library to extract tables from PDFs, used at places like NASA, Stripe, Figma. You can check them out at the link up top, vinayak.io/code. I'm also part of the Recurse Center, which is a programming retreat in New York City, where you spend 6 or 12 weeks programming at the edge of your abilities. It just requires investment of your time and nothing else, so if you're in a position to do it, I'd really recommend being part of a batch. If you have any questions about RC, you can catch me after the talk. So getting back to the main subject, how did I start thinking about running every street in Paris? A couple of years ago, I stumbled upon the PackTom project by Tom Murphy, where he ran the length of every street in Pittsburgh, which is 2,400 kilometers in total. He finished the project in 2022, covering close to 6,000 kilometers in 269 runs across 2 decades. It took him a long time because he was working with the constraint of starting or ending the run at his home, basically. So I started looking for other people doing the same, and found Ricky Gates, who ran every single street in San Francisco. He, on the other end, finished the project in like just 45 days, perhaps because he wasn't operating under the same constraint as Tom. So I started thinking if I could run every street in Paris. I moved here in 2021 and love how walkable the city is. I'd been doing the same running loops, and it had gotten a bit monotonous over time, and I thought it would be a fun challenge to run every street in the city. So Tom Murphy and Ricky Gates had a bit of a manual approach, so I also thought it would be fun to automatically track my progress as I run, as it could be a fun side project and a way to learn about GIS, which is another thing I always wanted to do. So I came up with this initial approach: fetch the street network from OpenStreetMap, compute the minimum number of 10K routes that could cover every street in the city, run them, automatically match my streets to my runs to the street network, and then visualize my progress. OSM, for those of you who are not familiar, is a free and open map database updated and maintained by a community all around the world. It was very easy to fetch the street network for Paris from OSM with a library called osmnx, which we'll look at later. But calculating the minimum number of 10K paths that can cover every street in Paris turned out to be a bit challenging. I discovered that what I was trying to do was essentially a variation of the Chinese postman problem, where we need to come up with the shortest route that can cover every street in a road network. At this point, I was spending a lot of time wrestling with the data I got from OSM and not a lot of time running, so I decided to tweak my approach. I thought that initially I can just draw these routes manually, build out the rest of the system to match my runs and visualize the progress, and then eventually get back to computing routes automatically. And now, like, I've built something where whenever I upload my run on Strava, it sends a webhook to my server, which updates the description of my Strava run. And as you can see, I've covered like almost 30% of Paris at this point. I've also built like a way to visualize like my progress. So this is where I'm at right now. I've covered almost 30% of streets, and maybe I can give you a short demo if I can figure out a way to. Okay, so it basically shows all the streets I've run, which are marked as green, and all the streets that I haven't run. I can draw. It's hard to draw looking at it that way, but I can basically look at the streets that I haven't run on, start drawing a route, put it on my watch, and then start running. And so if I go back to the presentation, if you want, you can check out my progress too by going to this public link. I put in like a QR code which should make it easy for you to access it, where you'll see the same zoomable map of all the streets I've covered. So before going into the implementation, let's take a step back and talk about GIS, because what I've essentially built is a geographic information system. GIS is a framework for gathering, managing, and analyzing spatial data. These systems are used everywhere, from urban planning to logistics, et cetera, just like a lot of applications. When working with spatial data, we need to understand coordinate systems. There's mainly two types: geographic coordinate systems, which use latitude and longitude, like WGS 84, which is World Geodetic System 84, which is what our GPS uses. And then we have projected coordinate systems that flatten the Earth onto a 2D plane, like the Mercator projection, which you might remember from school. Each has trade-offs. Geographic systems are great for GPS, but projected systems are better when you need to calculate distances and areas more effectively. There are two main ways to represent spatial data. Vector data represents features as points, lines, and polygons. Think of it as drawing with geometric shapes like you would do with an SVG on the web browser. On the other hand, raster data is like a grid of pixels, basically like images. Vector data is perfect for discrete things like roads, buildings, or city boundaries, whereas raster data works great for elevation maps, temperature, or satellite imagery. For my street running project, I'm mostly working with vector data. So let's break down the basic building blocks of vector data. Points represent single locations. For example, the location of this conference center, or like the location where I started my run. Line strings are paths or routes, perfect for representing streets or running, or like the complete run, basically. And polygons represent areas like parks, buildings, or even an entire city. These are the fundamental geometries, and we can combine them into more complex shapes like a multi-point or a multi-line string, but we won't cover that in this talk. Now let's talk about GPX. So when we record a run using a GPS watch or a phone, the data gets saved in this file format called GPX, which stands for GPS Exchange Format. And it's basically an XML that stores the coordinates of your run. So I guess if you look here, we have the lat long, we have the elevation, the timestamp at which it was recorded. And this is the raw data that I get from my runs that I need to process and match against the street network to finally visualize the progress. And most fitness apps like Strava, Garmin Connect, or Apple Fitness can export data in this format, basically export your runs in this format. So where do we store all the spatial data? That's where Postgres and PostGIS come in. Postgres is this incredibly powerful database which has been around forever, basically, and PostGIS is an extension that turns Postgres into a fully fledged spatial database. You can enable it in Postgres by just running create extension PostGIS. And it adds these data types that we just talked about so that we can store points, lines, and polygons directly into Postgres. Plus, it gives us hundreds of spatial functions like calculating distances, finding intersections between two line strings or two geometries, checking if a point is inside a polygon, etc. There's just a bunch of them. So I guess with those building blocks in mind, we can start looking at some code. So if I go here, I mentioned osmnx at the start. This is the library we can use to get the street network for any city out as a graph data structure. So we import it with import osmnx as ox. We can then use the graph from place function, put in the city name, and since we want to run every street, we put the network type to walk. The thing that we'll get back is going to be a network X graph, which I can show you now. So as you can see, I have this helper function, and it's displaying the full graph for Paris. And if I zoom in, you'll see that it's very dense because there's a bunch of streets to walk on, but also that every street has two edges, which is a bit overkill for what we are trying to do. And it also just makes it a bit harder to process this graph data structure. Ideally, we'd want to have just one edge per street so that it's easier to process the whole thing. So what we can also try is specifying the network type as drive, which should hopefully prune our graph. And when we look at that one, It removed a bunch of edges here and in those parks because cars can't go in there. And so if I now zoom in, we can see that every street is a single edge, which is a bit easier to work with. But if I go to like maybe another area, for example, this one, you can see that there's some streets that we haven't gotten because cars can't go there, but I can still run there. So like we still need a way to like get those streets somehow. So I was researching like how to do that and like other people who might have done things like this, and came across this repo by Matej Kerkreti, where he's defined this really complex custom filter, because you can filter OSM data with like like different types of filter. In here, we are basically excluding toll roads, private roads, all of those things. And if we use this filter by just passing in custom filter like that, we'll get a much better graph. And if I go back to the area I was showing, you can see that we have the streets that we previously didn't get. So yeah, it's a better graph to work with. We then convert that graph into a geodata frame. We can do that using the graph2gdf function. We don't really care about the nodes, just the edges, so we set nodes to false, edges to true. And this will give us streets, which is a geodata frame that looks like that. We'll have an OSM ID for every street, the highway type, the name of the street, the length, and most importantly, the geometry, which is a line string, which is connecting two points that I just showed you. So I guess as with any data project, there's a bunch of data cleaning to be done. There's a bunch of nans in the street names, and some of the street names are also lists. So we need a way to fix that. And what I wrote is this simple ensure string function, which converts the list names into like just one single name, which is a string. And also name all the nan streets. For example, if there's 10 nan streets, I name them like unnamed street 1, 2, 3, and so forth, so that we just have different streets to work with and not just like a single name. And so if we apply both of those transformations, we'll see that all the nans and lists are gone, and the data looks a bit clean. But then there's this thing where the streets that we get back from OpenStreetMap, they can sort of lie in the data frame as different segments of the same street. And so we need a way to combine them, because if there's a really long street, you can sometimes have 3 segments of the same street. But what we care about for our matching is just one street. And to do that group by, we can use this dissolve function from geopandas, where we group by name. And what it basically does is combines all of the different geometries by name into a single geometry, so that at the end we only get one street. So if we do that, you can see that all of the duplicate streets are gone and all of their geometries are combined. Now we can start inserting this data into Postgres. So here I'm just creating a session into a Postgres instance running on my local machine. I've already created a database called Terrace. This is the streets table that I want to create. I've defined an ID column, which is going to be the primary key of this table. It's going to be an auto increment field. For now, I'm just storing about the name of the street and the geometry, which we need to specify as a multi-line string. We can also store like the OSM ID and all of those other things, but I guess for the purpose of this talk, I'm just going to go with these 2 columns. So then we can iterate on all of the unique streets that we found and start inserting them into a table. And in the end, when we query the table, we can see that we found around like 5,400 streets. So now we are ready to do map matching. So if I go here, let me just grab some water real quick. So I did the short run and downloaded the GPX file for that run. And the way we parse that GPX file is using a library called GPXPy. It gives us a GPX object with tracks, segments, and points. And what we're doing here is basically like iterating on all of those and creating one single line string, and basically appending like the points into this run points array. I'm not sure where my mouse is. OK, yeah, here. If we plot that, you can see that since the GPX like trace can be a bit noisy, like it's not all accurate all the time because buildings are high and sometimes your watch doesn't record the most exact point. That's why it's sort of like we are basically getting the point on that building. It's not like I'm Spider-Man. I wish I was. But like the initial GPX track that we get from a run is going to be like that, very noisy. So the first thing we need to do before map matching is adding a bunch of points to sort of increase the resolution of our run. And to do that, we can basically insert 1,000 points along this geometry that we found and use the .interpolate function to add these points at a uniform distance. So after we run that, you can see that we have a more uniform run. It's going to be easier to map match it because it's more uniform. And if I zoom in, you can see that it inserted a bunch of points between all of those points that we recorded in our run. And so now, like it's sort of like the same thing that we did before. We create a connection into our database. We have the streets table. We have around 5,400 streets that we already inserted. And we basically write this match points to street function. So what we are doing here is we are creating this empty street points dictionary. We are iterating on the run points that we just created. We then run this query to sort of get the street that is nearest to our point. And we are doing that by using this st distance function from PostGIS. So we are ordering all the streets by the distance between the point to that street and fetching the first one. And this should give us like the nearest street to that point. If we find the nearest street, we initialize street points with like another dictionary for that street. Here we are just putting like the street geometry and a points array, which is somehow not visible. It's being cut out, but you can assume it's there. We then get the street geometry and do another interpolation where we are projecting the point to that nearest street. So it's sort of like snapping that point to the nearest street. If, for example, this is a street and the point lies here, this projection would project it to the nearest street, and we'll get a projected point, which we then append into our points array. And if we look at the next slide, we can see that we found two streets, Notre Dame de Lorette et Lafayette. And if we plot those, we can see that all of the points from that noisy run that we initially got, they've been snapped to the nearest street, which is what we wanted to do. And so now we need a way to store these sort of matched streets into our database so that we can eventually look at the progress. And to do that, we're going to create a new covered streets table. And it looks very similar to like the last table that we created. The only difference is that it has a progress percentage where we're going to store the progress for that street that we run on. So we iterate on the street points dictionary that we just created. We get the line string of that street. We create a new line string from the points that we projected onto that street. And we can now get the progress by dividing the length of the covered line string on that street by the length of the line string of that street. We basically then initialize a covered street, add the covered street here, and you can see that it's giving us a nice progress. So that curved street that we saw, we covered almost 95% of it, whereas the other one, it's still at 30%. So if we go here, you can see that it's correct because this is the straight line that is Notre Dame de Lorette, and we've only covered 30%. And this curved street that we are looking at, we sort of missed that tiny bit of it, and that's why we don't have 100%. But what I'm doing to sort of mark a street as covered is I assume it's covered if I've covered 90% of it. And so just based on that metric, we can say that after this initial run, we covered one street, and we're still left with a lot more. So now I assume I did a second run. I parse all of the points again, like we saw before. These points lie on the same Notre Dame de Lorette street, but they lie a bit up. They are still very noisy and inaccurate, so we need to do the same matching and interpolation. So first we do the interpolation. We get a nice uniform GPX trail. We then do the same matching. I see I don't have a lot of time, so I won't explain it again, but it's the same query that we're running on our database using this st-distance function. We can see that we only found one street this time. These are all the points that have been snapped to that street, which is what we're looking to do. And this time, this for loop on the street points dictionary looks a bit different because we are looking for an existing street that we've already covered by name. So when we iterate on street points, we see if there's already a covered street with that name or not. If there is, we combine the line strings of the covered street with the line string of the street that we covered. Sorry, there's a lot of covered, but I assume that you understand what I'm saying. So we combine the new run with an existing geometry, and based on that, we can create the progress like that we've covered on that street now, and insert the updated geometry into our table. So if we do that and plot the covered streets, you can see that we've now covered like around 60% of the street that we initially inserted. The progress is still 1 because as I can show you, we've only covered 60% of Notre Dame de Lorette, and we won't mark it as covered until it's 90. And now I think, so that was basically like the map matching, and now I can get back to the main slide. So yeah, I guess it's been super fun to run every street in Paris and explore new neighborhoods that I otherwise wouldn't have explored. Not sure if I could do the same in Delhi, where I'm originally from, because it's super huge. I actually tried visualizing the street network for Delhi in my browser, but it crashed my computer because it's just so big. And so, yeah, let's talk about some future work. The simpler approach has some trade-offs. Like if I show you this image up there, if I run through like a star intersection, if I'm sort of coming from that street and then I cover this circle here and go to this street, it can sometimes match those two streets because of the inaccuracy, and not the inaccuracy in the GP extract, but the st distance function that we're using. Because when I'm running here, it might find that street in the query that I just showed you. And I want to try using the Viterbi algorithm to solve that. It's sort of like an algorithm that uses hidden Markov models to sort of find the most likely path, and maybe that'll like improve the map matching. But I guess for now I can live with that trade-off because I anyways won't mark those two streets as completed, and I'll eventually run over them in the future. I also want to look at into computing routes automatically, the thing that I was trying to do before, like the Chinese postman problem I touched on earlier. And hopefully, I'll have full coverage by this time next year. And that's mostly it. Thank you for listening. You can reach out to me on those links.
Thank you so much. That was great. Do we have any questions about Paris running? I'll start here and then pass over there.
You can, let me just go back to, I sort of didn't show all of those slides, but yeah, this is where you can find the slides for the talk. And that is the link where you can look at the zoomable graph for my runs, my progress.
So it's not a technical question. It's more a question coming out of concern. Do you think it's safe to run every street in Paris?
I think so, as long as you can run them during the right time of the day.
Hi, super cool project, thank you. I was just wondering, why did you need to do the interpolation between GPS coordinates? Wouldn't the discrete coordinates also be enough to map them onto the street and then identify?
I initially sort of was doing it to sort of improve like the matching accuracy because like in my initial approach, I was also looking at like maybe 10 points in the future, like after and 10 points before, and it sort of improved the accuracy a bit. But yeah, maybe for this approach, we don't really need it. But in general, I'm new to GIS, but I sort of read that it's a really it sort of like improves the accuracy, and so like it's a nice sort of thing to do before you do map matching.
Thank you. Do we have any other? Okay, there's one. Or you can also line up behind that mic.
Would you recommend doing this in your own city, and how often do you get lost? Very fun talk, by the way.
I mean, I recommend doing it in every city. I think like European cities are like really nice to do this in because they're like smaller compared to, I guess, the US or India or like other places in the world. And I guess in terms of getting lost, I think at this point I know like Paris really well, so I don't really get lost. But then if I get lost, I can always pull out my phone, and I also have like the track that I create on my watch. So I'm just always looking at my watch and running in like on the track that I created on my computer. So yeah, it's hard to get lost, I would say, especially in Paris. But I don't know about Prague. Maybe Prague is an easier city to get lost in.
So do you have some algorithm that designs your runs, right? Like you have a thing that like will tell you where to run next.
I'm still working on it. Right now I just do it like manually. If I go here, I'm just sort of clicking and looking at the streets that I didn't run on, and then at the end I can download the GPX file, and then I can just put it on my watch.
Okay, thank you. Any other running geo questions here?
Do you parse every run manually, or do you have some automation on it?
Now it's a webhook, so I guess if I can go to that slide from before, like I get a webhook from Strava every time I do a run, and it hits my server, and I sort of do the map matching and everything automatically and update the description. So every time I finish my run, now I automatically get the progress.
Cool. How?
Yeah, thanks for your talk. It's really awesome. It's a great idea. And unfortunately, maybe there's also already a commercial app for that. It's called Wanderer.earth. That's probably exactly doing what you're doing. But yeah, it's really great.
Yeah, I think I tried using city strides and Wanderer initially to do this. But I guess like the matching wasn't very accurate, and like the street network that they were showing me, it didn't have all the streets that I wanted. So since I wanted to just learn GIS, I was like, oh yeah, it's going to be the perfect project for me to do myself.
Thank you. Are we done with the questions? Okay, thank you once more time. Thank you.